From his earliest days of construction, man has recognized the need for a dependable foundation. Piles have played an increasingly vital part in meeting this need as man has conceived and built more complex and heavier structures with progressively less choice in the site selection. Since the first timber piles were used many years ago, several pile types have been developed to meet the increasing demand for increasing performance. Foremost among these is the cast-in-place concrete pile, consisting of a steel shell driven into the ground, left in place, and filled with concrete. Since the original cast-in-place pile was introduced over 60 years ago by Raymond Concrete Pile Company, several variations have evolved until today our company offers the widest selection of pile types to best satisfy design and construction conditions. Time does not permit us to review the full range of Raymond's foundation service, nor completely cover the field of pile foundation design and installation. We can only present the methods and materials for the principal Raymond piles, together with their design features and general application. Through the company's 20 offices, located in principal cities throughout the United States, Raymond can combine a knowledge of local conditions with its general experience to apply the proper methods, equipment, and pile type to fulfill the individual job requirements. Steel shells, which are basic to all Raymond cast-in-place concrete piles, are manufactured at our Youngstown, Ohio plant and shipped directly to jobs or to strategically located storage yards. At such a yard, mechanical equipment unloads and stacks shells according to size and gauge. From here, the shells are shipped to jobs in the area served by the yard. On a countrywide tour of representative jobs, we reviewed the fundamentals of Raymond piles. At a New York Idlewild Airport job, test borings had indicated the use of friction piles, and Raymond standard piles of heavy uniform taper were a logical choice in the foundation design. Piles are often classified according to the apparent principal means of support, such as point bearing or friction. However, no sharp boundaries exist between the two types, since the soil usually supports the pile by some combination of friction and direct bearing. For the essentially friction pile, a tapered pile is generally preferred since it develops a capacity by both friction and direct bearing along its full embedded length. The standard pile has an 8-inch point and tapers to a diameter of 22.8 inches at the butt in its maximum length of 37 feet. The bottom is closed by a flat steel plate welded to the boot assembly. This detail shows the thin gauge steel shell reinforced internally with a wire, spirally wound around a 3-inch pitch. This provides strength against collapsing pressures usually resulting from the soil displacement. The wire is set in grooves to permit full contact between shell and driving mandrel. In its expanded position, the mandrel firmly engages the shell and serves as an efficient tool to drive the light gauge shells to proper resistance. When the driving has been completed, the mandrel is contracted to permit withdrawal without disturbing the steel shell. Thus, the shell, left in place, maintains all the resistance to penetration built up during the driving. The result, a steel-encased hole which can be readily inspected its full length before filling with concrete. The steel shell also serves as a form to protect the fresh concrete during its critical setting. This assures a continuous concrete shaft of full cross-section. At the work site, the 8-foot shell sections are prepared for assembly on the expanded mandrel. Sufficient sections are placed on the mandrel to make up the required pipe length. Lapped joints between shell sections are wedged tight during driving. The shell assembly is completed with the placing of the boot section on the mandrel, and the rig swings into driving position. By adjusting spotter length and boom angle, the leaders are inclined to the required batter, and the pile tip is carefully centered over the location stake. Normally, foundation piles are driven vertically, but batter piles are sometimes required to resist high lateral loads. These standard piles are used principally as friction piles, applicable to all soil types where the required capacity can be obtained within the available pile length. Because of its heavy taper, this pile will often develop higher capacity for equal length or equal capacity for shorter length than piles of less taper. After required driving resistance is reached, the mandrel is contracted and withdrawn, leaving the shell in the ground. Leaders are returned to the vertical for the next shell assembly. The driven shell is now ready for internal inspection to check on the alignment of the pile and for possible damage. All piles are vulnerable to misalignment or damage during driving, and unless the pile can be examined after it and adjacent piles have been driven, such damage could go undetected. To facilitate inspection, artificial light or reflected sunlight may be used. With excess shell cut off, the remaining shell is filled with concrete to complete the pile. As we resumed our tour bound for Miami, we caught an excellent view of the greater New York area, where, if we could pick them out, we could find approximately 2,000 structures of various types resting on Raymond foundations. In Miami, step taper piles were being driven for a new bank. The choice of pile type was based on test boring data which indicated difficult driving and also the structural design which required the development of high-capacity piles. This pile tapers in steps to the rate of 1 inch per length of shell section. These sections are normally furnished in 8 and 12-foot lengths, although 4, 16, and 24-foot sections are available to meet special conditions. Joints are screw connected by means of a collar welded to the driving ring at the bottom of each section. The pile point is closed by a flat steel plate. This detail at a joint between sections shows the driving ring which engages the corresponding shoulder or step of the mandrel. The steel shells are driven using a heavy rigid steel mandrel which bears on each driving ring, including that at the pile tip. When driving is completed, the mandrel is withdrawn and the shell is left in place ready for internal inspection and concrete filling. All driving resistance is maintained, and the shell, corrugated for strength, serves as a form to protect the fresh concrete. Step taper shell sections are usually assembled on a horizontal rack to make up the required pile length, although assembly can be made on the mandrel. The screw collar on each shell section is coated with a mastic to assist in waterproofing the joint. The shell sets are marked off every foot to facilitate logging the pile, that is, recording the number of hammer blows required for each foot of pile penetration. Screw connections between shell sections are drawn up tight, and complete shell assemblies are stored ready for driving. The presence of an upper crust of coral rock required pre-drilling in advance of pile driving. The actual driving cycle starts with the placing of the shell on the mandrel. To bring the top section under the mandrel tip, the shells are lowered into a previously driven pile. In most cases, this permits shelling up with a full set in a single operation. The pile is lowered into the pre-drilled hole and driven to its final resistance. The step taper pile has great flexibility in meeting both design requirements and site conditions. Usually, the controlling pile dimension is the butt diameter, for which this pile offers a wide choice up to 17 inches. The combination of butt diameter, pile length, and shell section length will control the point diameter, which can range from 8 to 14 inches. Normally, 8 to 10-inch points are used, with the larger diameters available for special conditions. After required driving resistance is reached, the mandrel is withdrawn and the shell filled with concrete to proper grade. Internal inspection, of course, precedes the placing of concrete. The general contractor's work on pile caps can follow immediately. En route to Los Angeles, we visited New Orleans, where there was ample evidence of Raymond's activities in foundation work for highway bridges, as well as many other types of structures. Over 2,800 step taper piles were driven for this exceptional interchange structure carrying the Lake Pontchartrain Causeway Boulevard over the Airline Highway. Raymond piles support many expressway structures in the New Orleans area, as well as structures throughout Louisiana's progressive highway system, such as this pre-stressed concrete bridge, the Wisner Boulevard overpass. Another example, a cement plant along the Inner Harbor Navigational Canal. Also, this lift bridge crossing the canal. This bridge received the American Institute of Steel Construction Design Award for 1959. Raymond's part in highway work has kept pace with the increasing activity of the National Highway Program as more and more states realize the advantages of our products and methods. At a tank farm in Los Angeles, we inspected another example of Raymond's diversity in pile types. Here, one of our crews was driving composite piles, consisting of a lower section of untreated timber driven below the permanent water table, and an upper section of cast-in-place concrete. This pile can be driven in two stages. The wood section first to its full length, followed by a set of step taper shells driven with a mandrel. With the necessary embedment and final resistance reached, the mandrel is withdrawn, and the shell, remaining in place, is inspected and filled with concrete to form the finished pile. The lengths of timber and concrete sections used are governed by the required total length of the pile and the depth to the permanent water level. For normal loading, the recommended joint between timber and concrete is the tenon type. During driving, the follower, or mandrel, fits over the tenon and engages both its top and shoulder. In the finished pile, this tenon extends into the concrete. A special sealing ring at the bottom of the step taper shell section fits tightly around the tenon to exclude water during placing of concrete. Where the joint between wood and concrete is subject to tension, such as with uplift forces, the rod, pin, and socket type is used. The pin anchors the socket, into which is threaded the rod, which extends through the concrete. The timber sections are moved onto the heading rack, where the tenon will be formed. First, a hole is drilled in the center of the pile butt. This is to guide the special heading machine. The electric-powered tool is brought up into position. The pivot bar inserted in the drilled hole. As the machine rotates, it cuts the tenon of required length and to proper diameter. The plain tenon joint, as in the example, the operation is complete. But however, for the rod, pin, and socket type, the transverse hole for the pin is drilled after the tenon is formed. Then, the pin and socket assembly is inserted. The prepared timber sections are stockpiled and are ready for driving. Several wood sections are driven their full length before the shell sections are added. However, the pile can be driven as a single unit, shell and timber together. In either case, the follower, or the mandrel, fits snugly over the tenon and bears on both the tenon top and its shoulder. The step taper shells with the ceiling ring on the bottom section are assembled into full-length sets for the second phase of the driving. However, in this case, only one 8-foot shell was required to bring the top of the timber section below the water table. With the wood section driven, the shell set is placed in position over the tenon and the ceiling ring under weight of hammer and mandrel, forced down to form the tight joint. Driving is resumed, and when final resistance is reached, the mandrel is removed, leaving the shell in place to protect the concrete filling. This provides an economical pile for relatively long lengths and light loads, usually limited to the capacity of the timber section. The use of a concrete upper section saves costly excavation, sheeting, and pumping that may be necessary to cut off and cap untreated timber piles below the permanent water level. Normal concreting procedure follows after internal inspection of the shell. To ensure filling the space between tenon and shell, suitable size aggregate is used. For the rod, pin, and socket joint, the reinforcing rod is installed just before the concrete is poured. Excess pile shells are cut off either before or after pouring concrete to grade, and the completed pile foundation is then ready for the structural mat. While in California, we visited a department store job in Los Angeles where a Raymond small universal rig was driving step taper piles. This gave us further opportunity to investigate reasons for the wide use of this pile. Although short piles are being driven here, the available length of the step taper is about 100 feet. Maximum length is actually limited by the capacity of the driving rig. This pile is used as friction, end, or point bearing under all types of soil conditions. The use of our rigid mandrel permits effective hard driving and the development of high capacity without injury to the finished pile. The mandrel also permits the proper driving of thin wall shells with the obvious savings in materials cost, without sacrificing any factor of safety. Not far away, a Raymond internal hammer core mounted on a small crane was driving step taper piles for a highway bridge. This highly mobile equipment combines in a single unit a step taper mandrel and a pile hammer developing 15,000 foot-pounds. During our tour, we noticed the use of sufficiently large hammers to meet design requirements and subsoil conditions. With our heavy, rigid mandrels, hammer energy is effectively transmitted throughout its length with minimum losses due to elastic compressions and vibrations. This combination of adequate size hammer and rigid mandrel results in maximum hammer energy available to mobilize the soil capacity. In the final analysis, the foundation load is carried by the soil, and therefore the capacity of the soil rather than the structural capacity of the pile is usually the limiting factor. The importance of mobilizing this soil capacity with the required factor of safety is obvious. However, the concreting operation is as important to the overall pile installation as the driving. After internal inspection and removal of excess shell, about 1 foot of neat grout is placed in the pile point, followed by concrete of proper slump, poured through a funnel having an 8-inch diameter discharge. Each shell is filled in a continuous operation to grade. Since the pile is not completed until filled with concrete, correct concreting procedure must be followed. Otherwise, proper driving of the shells is meaningless. During the critical setting period, the steel will protect the fresh concrete, maintain the full cross-section of the pile. Under normal foundation loads, no reinforcing steel is required in these piles, since for completely embedded piles, soil of even toothpaste consistency provides sufficient lateral support to eliminate column action. On the way to Detroit, we stopped in Chicago for a brief look at Raymond's work on the Illinois toll road structures. For several grade separations, step taper piles, both vertical and batter, were being installed for abutment foundations, also using an internal hammer core, but in this case without leaders or guide beam. Since the hammer is inside the top portion of the mandrel, alignment of hammer and pile is always assured. For intermediate bents, Raymond cylinder piles of pre-stressed concrete served as both the foundation and the pier column. 36-inch hollow piles with design load up to 200 tons each were installed by about 6 different methods, depending on the type of soil. For the driving method, the hammer used developed over 40,000 foot-pounds of energy per blow. In the Detroit area, noted for its deep strata of soft to medium clays, Raymond's wet rotary pre-excavation process was being applied. It is sometimes necessary in cohesive soil to reduce or eliminate ground heave or displacement which may result from pile driving. Normal pre-excavation methods are impractical in this type of soil, thus the use of the wet rotary process. As usual, the step taper shells were being assembled into sets. Before driving operations were resumed, we looked over the special equipment used in this process. Mounted at the bottom of the leaders is a power-driven table which rotates the drill stem and bit, and through which the hollow stem passes. A special swivel connection is used between the stem and the hose from the circulating pumps. Before pre-excavation starts, a set of pile shells is placed on the mandrel so that immediately after the drill bit is withdrawn, the rig can be swung into driving position and the pile lowered into the pre-excavated hole. The basic shell-up procedure is routine, but in this case, it was necessary to assemble additional shell sections on the mandrel to make up the total length required. The drill bit is carefully centered over the pile location stake, and the wet rotary process begins. It's a combination of rotary drilling and jetting. During drilling, the jet water is pumped through discharge ports located at the sides of the large fishtail bit. The upward flow of water carries soil cuttings to the ground surface. Various other methods of pre-excavation are used in pile driving, such as pre-drilling, as we saw on the Miami job, jetting, augering, and the dried tube process. However, each method is dictated by certain soil types and depths. As in the soft clay of this case, an augered hole would tend to close in. and jetting alone would open only a small hole, but the combined process assures satisfactory results. With the jet water flowing, the rotating bit is lowered into the soil. Soil cuttings and jet water carried to the surface are channeled into sumps and removed from the building area. Depths up to 100 feet have been successfully pre-excavated by this method. For positive ground displacement control, reaming blades of various sizes can be attached to the drill stem at proper intervals, thereby shaping the hole to the general configuration of the pile. By such accurate methods, soil displacement can be held to a minimum. When the drill stem is withdrawn, the resulting slurry of clay cuttings and water keeps the hole open while the pile is being lowered. After the pile is penetrated under the weight of hammer and mandrel, it's driven to its required final resistance, as is done with all types of pre-excavation. Again, of course, the normal procedures of inspection and filling shelves with the concrete follow to complete the pile. Back in New York City, we visited the construction site of the Bruckner Boulevard Elevated Expressway, where 4 Raymond rigs were driving pipe step taper piles. For this pile, we combine a lower section of steel pipe closed at the bottom with a flat plate and an upper section of step taper shells. Lengths of pipe and shell portions can be varied to suit subsoil conditions and total pile length requirements. The sleeve on the bottom of the lowest shell fits over the pipe to form the joint. When driven to required resistance and mandrel is removed, the pile can be visually inspected its full length, after which both pipe and shell sections are filled with concrete to complete the pile. This provides an inspectable high-capacity pile of unlimited length. To save on pile materials cost, the maximum practical length of shell section is used. Where necessary, the mandrel is expanded some distance into the pipe to maintain alignment between pipe and shell sections. Pipe of sufficient wall thickness must be used to prevent excessive energy losses during driving resulting from elastic deformation of the pipe. A detail of the joint between pipe and shell shows the sleeve welded to the driving ring of the lowest shell. Various methods are used to provide a watertight joint between sleeve and pipe. As indicated, the pile can be driven with the mandrel extending only to the top of the pipe. When the mandrel extends into the pipe, a relatively close fit between pipe and mandrel is provided. Pipe and shell sections are filled with concrete in a continuous pour to form a monolithic shaft. The step taper sections which form the upper part of the pile are assembled on the shell rack into full sets and stored convenient to the driver. As the crew prepares to shell up, it's readily noted that normal handling stresses are of no concern and a one-point pickup is sufficient. With the set of shells in the leaders, the rig swings over to pick up with another line the pipe section which is to form the bottom portion of the pile. Our universal driver, one of the larger type rigs, is equipped with a moonbeam at the bottom of the leaders for driving side batter piles. Normal shelling up procedure follows, with the set of shells first lowered into a driven pile until the top shell clears the bottom of the mandrel. After the shells are pulled up onto the mandrel, the pipe section is joined to them. We note in this case the mandrel extends into the pipe section for alignment. Such a rig can handle the full pile length, shell and pipe, as a single unit. If necessary, the pile can be driven into 2 stages, pipe section first, followed by the step taper shells. With the shell-up operation completed, the rig is positioned for driving. By adjusting the boom angle and the length of the telescopic spotter, the required batter is obtained. With the pile tip carefully set on the location stake, the driving gets started. The pipe step taper pile is used for both end bearing and friction, where the required length of a high-capacity pile is beyond the limit of available equipment for driving all shell step taper piles, or where subsoil conditions indicate their use. Since the pile can be driven in 2 or more stages, it permits driving longer piles than the equipment could normally handle, with the resulting extra flexibility of length to meet unforeseeable conditions. With the pile driven to required resistance, the mandrel is withdrawn, leaving the pipe and shell in place to maintain the driving resistance and act as a protective form for the concrete filling. In contrast with the Bruckner job, our work here involved driving only a few pipe step taper piles for a pedestrian bridge over the East Side Drive. With traffic temporarily rerouted, the once busy thoroughfare made an ideal construction site. With minimum interference with nearby traffic and with maximum efficiency, the job was organized and work was soon well underway. On the tour, we observed the general use of flat closure plates on the pile tips. Experience has shown that the use of a flat plate, especially with the mandrel bearing on it, permits driving piles harder and straighter with less deflection than with conical or tapered points. But not all construction sites in the city are as open as the one we just left. More typical is this site, where workspace is at a premium. Our pile driving operations were hampered by the large amount of shoring and bracing, and the 15-foot high cribbing on which the driver worked contributed to the difficult conditions. The art or science of pile driving, the application of engineering principles, and the development of special equipment and methods have advanced far beyond the primitive operations still employed in some quarters of the globe. Through a continuous research and development program, we strive to expand the knowledge of pile driving and to apply the technical advances in soil mechanics to the complex problems of pile foundation design and installation. In sharp contrast with primitive methods, we have adopted many of the marvels of modern science, among them the electronic digital computer, to solve the basic problem in pile driving. What happens when the hammer hits the pile? It has been recognized that the action between hammer, pile, and soil is a problem in wave stress transmission rather than one of Newtonian impact, which is the basis of most dynamic formulae. This model shows approximately how the pile acts under the hammer blow. The flexible spring reacts slowly enough so that the wave action can easily be followed. When the blow is struck, the stress wave produced moves down the spring and is reflected back. Additional reflections occur, but of less intensity. The action of a pile is basically similar to this, since the pile also is an elastic body of considerable length. However, in the pile, the wave action is much more rapid and forceful than in this spring. The pile material and its ability to resist elastic deformations determine the effectiveness of the hammer blow. The more resistant to elastic deformations, the more effective the blow. However, other factors such as driving stress distribution between pile and soil must be considered. Contributing to the complexity of this problem are the variations in soil profile, pile type, material, weight, and length, hammer sizes, type cap block and design load. A factor often overlooked, which influences the effectiveness of the hammer blow, is the type cap block used between the hammer ram and the pile top. The cap block is necessary to cushion the destructive impact of the hammer, but it must be capable of transmitting the available hammer energy to the pile without excessive loss. Excessive dampening of the hammer energy through the cap block seriously reduces the energy which develops the pile capacity. This would tend to invalidate the requirements of a pile driving formula. To satisfy minimum requirements, the cap block should be a one-piece hardwood block with grain parallel to the pile axis and enclosed in a tight-fitting steel housing. However, the use of a proper cap block is meaningless unless the pile itself can effectively transmit the applied energy throughout its length. In the final analysis, the soil into which the pile is driven must carry the load. To effectively mobilize this soil capacity, the pile must be sufficiently rigid and of adequate cross-section. Energy losses due to elastic deformations in the pile can be quite serious and deserve attention. The simple mathematics of dynamic formulas is not sufficient to analyze accurately the complex action between hammer, pile, and soil. The proper application of the wave stress theory could provide a solution to this problem in which the effects of all variable factors are considered. With the complete program established, the digital computer can perform a calculation in about 15 seconds. Thus, it is practical to make a great number of such calculations under various sets of conditions. Although technological and scientific progress continues to expand the knowledge of pile foundation design and installation, the proper application of this knowledge depends on experience. Experience is essential to surmount the many problems inherent in this work and to apply methods and materials that will achieve an efficient pile foundation.